I'm Mirjam Kuehne from the RIPE NCC, and the measurements and monitoring that the RIPE NCC was doing during the World V6 Day were mentioned a few times yesterday during the panel, so I thought it might be interesting to just give you an impression or give you an idea of what we actually measured and give you some pointers on where you can find more information. We did one thing a few days or like a week before the World V6 Day, mostly targeted to end users where they could check if they will have problems on the day. And we called that IPv6 eye chart. And I'll show you an example where we actually fetched some images from servers, from various organizations that wanted to be listed. And then you could see if that works, if you... Well, let me just show you the example, and it's easier to explain. That would show up on the screen where everything was okay, and you had no problems with, reaching content on World V6 Day for people that switched on V6. And then there were like a few other options that one could see in case there were any problems. For instance, this one, would have been problematic, and then, we had some descriptions or little hints under the image what you could do to fix that before the day. Then there were some other kind of mixed brokenness, like where the end user couldn't have done anything, but should have probably contacted their provider. And that was it. There was the one thing. It's still running. People can still go to that site and see if they have any problems reaching other sites on V6, and we will keep that running, I think, for a while. Another thing we've done was just before World V6 Day and then during these 24 hours, we measured or we checked if who said on their Core A records. I don't know if you can see that. It looks better than on my screen here. Basically, the green in the middle, that's kind of the day. It's on 8th of June, and if you go to that site, you see a little time slider underneath. You can look back in time, and you can see here quite nicely how people switched on V6 and like on a midnight UTC, and then most people switched it off again. But you can also see that some organizations kept it running after 8th of June. So that's still on the website. We stopped collecting that data, but you can still see what happened during the day. And we could see it just as a snapshot here. We could see some interesting things happening just before. For instance, some people kind of switch it on and off and on and off, and we're like kind of testing before they actually switch it on at midnight. And we could see some other interesting things like the Google site, like some of our vantage points, they were whitelisted and others weren't, and so we didn't see anything there. Yes, that's what we've done. That's just an explanation of that chart I just showed you and how we measured that. And then also we're going to do some more analysis of the data that we collected, and we will put that on RBL Labs. And all the measurements are on that website there at the bottom that I showed you before. And then just at the end, just one other thing also on that side, and that's it looks like this. I just thought it was a pretty picture I wanted to show you. For those of you who know DNS-Mon, the DNS monitoring system that the RIPE NCC is providing, that works very similar here, just that it doesn't connect to DNS servers but to HTTP servers. And so all our vantage points, like all the measurement boxes we have out there, they were looking if they could reach those HTTP servers, and depending on that, each of these cells has a little color code, and you can see on the site how that changes over time. So that's actually all I wanted to show you, just to give you an impression of what we've been measuring on the day. It's basically Core A's and the HTTP. And then we also provided this eye chart for users to check if they will, or if they will see any problems on the day. And that's it.
Any questions?
Website again.
Okay, thank you.
Thank you.
All right. Okay, next up is Manish.
Hi, I'm Manish from the research group at Merit. What I'll be talking about today is network reputation, and in particular what we're doing to build towards a network reputation, in particular where we are starting from and what our early results are. Once again, this is really early work, hence the lightning talk, so feedback is very, very welcome. Let's start with the introduction and motivation. These are the really hard problems. How do you create incentives for people to run clean networks? How do you measure the relative security posture of a given network? How do you balance the need to communicate with another network with the risk? Because inherently there is a risk. More interestingly, how do you estimate the likelihood of a future attack or future malicious activity from a network given historical data or current data? Can you assign a risk metric to a BGP path? Hard questions. But what would help? What would help is if you had some historical and current notion of the behavior of a network from a security perspective, some notion of reputation. So that's what we're trying to get at. That's the goal. What are the properties? Well, we know one of the things that you should not do is rely on a single source of data, because then your reputation results will be biased towards a single type of activity. So you have to have diverse data sources: BGP, DNS, email, anything else, malware analysis, everything. You should be able to get a lot of this information passively by just watching traffic, watching routing. But you should also have a way of including public participation. In a lot of cases, there's information out there which is heavily dependent on vantage point. You want to have as many vantage points contributing to your sources of reputation as possible. Both global and local data sources is very important. It should hopefully not be the responsibility of a single entity to generate this reputation. It should be crowdsourced, taking as much input from the community, and be as distributed as possible. It should have mechanisms, for example, for local parties to weight or to emphasize or de-emphasize particular reputation that you may be providing them. And you should be able to merge global policy and then apply it on a local perspective. So here's the architecture. It's very simple. What you're seeing is basically four key elements of it. One is the third-party data reports, which are from external systems. Two are the participation reports from individual people or networks who participate in this reputation generation system. The third is some sort of a central collation agency which collects all this information. It could be a single entity, it could be a distributed group of people, but the core responsibility of this global reputation system is essentially to leverage some theory from mechanism design and game theory to do the right to set the right incentives for people to participate, to set the right weights of how do you value information from different people differently. And then, of course, the central authority should also have some way of disseminating this reputation once it's been generated. Let me quickly go over what the key components are. The external participation reports are essentially third-party data sources. In our context, these basically mean things like spam reports, RBLs, malware, IPs that have been identified from malware. They're generally published by a third party. And you have lots of host, and essentially what these reports are indicators of host reputation. And what we do from these is try to seed the network reputation from the reputation of these hosts. The second component is the participation reports. This is really hard. You have to have the right incentives for people to contribute honest reports and disincentives for people to lie. And this is where we're hoping we're going to leverage some background from mechanism design and game theory to set the right incentives in the system so that it is not easy to game. Here's an example of finally what it'll look like. The prefixes, every single prefix in the BGP table will have a reputation score from 1 to 100. And basically, what you will be able to do with it is set security policies. So what are some examples of security policies? If you had this reputation, what could you do with it? Well, for example, for BGP, you could compute paths. For each AS path, you could compute a relative reputation score for it, reliability or risk metric, if you want to call it that. And then you could set BGP policies saying, I don't want my packets to go through a bad neighborhood, or I want them to prefer this other path based on my analysis of how well these networks are run in the AS path. Spam scoring, this is already done to a large extent. Maybe you could tweak it a little by using network level information as well. Inbound firewalls could be much more than just a single accept or drop rule. You could have grayscale. So you could say, maybe send this, so maybe drop everything that's in the top worst 5%. In the next 10%, maybe I will send them to a DPI box and pay more close attention to that traffic, whereas everything that's in the best 10%, I'm going to just pass it through to my regular servers. Applications could make use of reputation as well. For example, if you're a bank, you could say, well, I'm going to block the worst 5%. The next 20% I'm going to send to a site which requires two-factor authentication. And the rest don't need it because I trust those networks. So if you have this information, it enables a whole range of activities which are much harder to do right now. So let's talk about how we're bootstrapping the system right now. We're starting with lots of third-party data. So BRBL, XBL, spam cop, they're all the spam data types, then the command and control data coming from Cymru and shadow servers. We're building our own data set for darknet scanners, activities coming from different networks. Brute force SSH attempts, we're collecting that data as well. And of course, drone BLs. All these lists have different magnitudes in terms of how many IPs are on those. And what we do is we take those and try to bucket them into prefixes and try to derive reputation scores based on those. Not sure if the lines are very visible on this graph, but essentially what we're trying to show is that all these RBLs, when you take all these individual IP addresses, you put them in, you bucket them by prefixes, you can get some notion of how many IPs in each prefix are on RBLs. And then you can sort of derive a relative dirty or cleanness of a network. This is a very, very preliminary notion of what a reputation of a network is. But it's a start. So let's take a look at some of the RBLs and geographically distributed country-wise bucketing. What do we see if we try to just bucket by countries? For example, here's the XBL. I'm just going to show the top 10s here. You'll notice top 10, India, Brazil, Russia, spam cop, pretty much the same set of actors, BRBL, same. What's different with this is the Cymru servers, different map. What we're seeing all of a sudden is United States, Germany, Canada, Japan. Shadow server, United States, Germany, France. What's the difference? What our conjecture here really is that the types of lists are different. The Cymru and the shadow servers are essentially reporting command and control infrastructure. And what it looks like from at least the content, for examining the contents of these lists, is that the command and control infrastructures are being based in the developed nations, and IPs that are countries, essentially the BRIC countries, which are the Brazil, India, China, Russia, are serving as the spam or the sender hosts, the ones that are the compromised machines, the ones that are sending out, they're being used to send a lot of email. The darknet scanners list is sort of a mixed bag. It seems to have IP addresses that are spread out fairly evenly. There's some overlaps in the data types as well, because we have to know what the overlaps between the different RBLs are. Cymru and shadow servers seem to have significant overlaps. The XBL and the spam cop seem to have significant overlaps. So we have to sort of take this into account when we weight reputation for networks. Here's an example of the BRIC countries, for example, and how often they show up in these different lists. And now what I wanted to quickly get to was an example where we're building a reputation score. If we take just 3 data sources and we weight them all evenly, this is the percentage of, and we build them basically on the percentage of the total IP addresses in a prefix that are on these lists, you can come up with some scoring or reputation index. And here I'm just presenting 3 data sources, the top 10 lists, and roughly resolving them to where their locations are. So it's hard to say whether this is definitive proof of reputation or not, but it's sort of trying to build that. And once you have prefix level reputation, what you can then do is you can build a notion of AS level reputation by aggregating across all prefixes. And here's a screenshot from our prototype system of the top 25 worst reputation ASs. So conclusion, the goal of the network reputations really is to create some sort of a predictive indicator of how well a network is run, and then allow for security policies that take that into account, the relative likelihood of future malicious activity from a network. If you have this information, you can use it for making sound policy decisions that affect the future, not just reactive policy decisions. This is still work in progress, so comments are welcome.
Michael Sinatra at ESNet. I said some of this yesterday. I'll just say it again. First, thank you for presenting this. This is a useful window into the data you've collected, the research you've done, and the methods you're using. I think that especially to the extent that you use reputation to derive policies, you will get into endless discussions about the quality of data, the models that you're using, and the inferences that you're making. So you have to be very, very careful. Of course, to the extent that you make that more and more transparent, you're going to get into more and more discussions. To the extent you make it more and more opaque, people will trust it less. So it's just a difficult tightrope to walk. And also, just be a little bit careful about how you use game theory, since it's not really a theory, it's a modeling method.
That's right.
And most game theorists will not call themselves game theorists, they will call themselves formal modelers, as someone who used to do that work. And so the important thing is that the theory behind it is good.
That's right. Thank you. So it's a good point that, and I do want to clarify on the game theory part. We were warned against going game theory because this is not a game. Inherently, what we want to do is a derivative of game theory, which is mechanism design. And what we're hoping is that that will give us a theoretical background for incentive setting and how the incentive should be weighted in the system to get honest feedback in.
But the important thing is the theory part and not the method you're using to derive it. You need to have a good theory starting out.
Right.
Hi, Chris P., Soft Layer Technologies. I was curious, are you getting your prefixes from like the PGP global tables, or are you breaking them down to 24? So if you're rating on what you're learning out of the tables, is it possible that with just a few hits you would end up, degrading an entire 15 or 14 and causing adverse traffic flows to those networks? Being in the hosting industry, we have a lot of customers that will just pop up and do bad things, and then we get rid of them, and then they reform themselves, and next time they come to us, we don't even recognize that it's the same customer. And again, we get hit, we take them out. But in your kind of method, it looks like a lot of our prefixes would just always be in kind of a negative rating.
Right. So the way we weight the prefixes of the reputation of a network is really how, as a whole, of the total possible hosts in it, how many of them were seen doing malicious activity of one form or another. This can also be weighted in different ways. If you're doing SSH brute force break-ins, well, maybe you want to weight that data more rather than spams, because we know that's not very reliable. So yes, there are different ways of weighting it. Our initial system does do purely a density of how full your network was in terms of badness.
Okay, we'll have Chris as the last question, and he'll be available, the speaker will be available afterwards. You can talk to him.
Sorry, Chris. I missed the beginning. Did you say how I can get access to this data, or how someone can get access to this data and the format in which the data comes?
We have not publicly released the website, but I can share that with you, and we can talk about it offline. But,
Okay.
but eventually, once we have a reasonable system built, we do intend to just distribute it over XML or download it.
Okay. Yeah, so it seems like this, again, we had this discussion yesterday, but the sort of making the data available in a fashion that enterprise folks could make use of it. I don't necessarily think that is it a /15 that got thrown away is a problem for the enterprise people as much as it is for ISP people. But
Okay. All right, so thank you. And next up, and I say you can grab them off to the side in the hallways. Next up is Anton.
All right, good afternoon. So what I've been working on lately was prompted by a friend at UW, and subsequent to meeting Paul Burford some time ago, we've taken upon ourselves to look at more measurements, more available data that we can chew through and think about. And so today we're talking about some work that we're doing, an ongoing work that's already begun, to look at roughly what's really happening in mobility in terms of usable and available performance, and specifically how does that compare to cellular performance. And we decided to start with one of the best, or not best, but I shouldn't qualify it like that. I should say one of the most prolific data sources we can find, which is speedtest.net. Who's familiar with speedtest, roughly? Probably all of you. So, you know, excuse me. You sort of roughly know how it works. It sort of tries to help you understand what's going on your connection. And the thought we were initially starting with in this work was, what is the real difference between someone who's rooted on a Wi-Fi type connection or someone who's using purely mobile cellular connections? So we started to process this data. In short, what this stuff really amounts to is a combination of some JavaScript and Flash applications that seek to do basic upstream and downstream assessments as well as some round-trip time. People who operate servers, providers rather, who operate the speedtest.net servers, which are publicly listed in the database, are provided the table you see at the bottom. It may not be easy to see, but the general idea is that a server operator understands who's hitting it through the eyes of this type data source, and through some sort of an EDI or web interface, you are given the results of tests that were executed against your server. You can also request of speedtest.net your own interested data. You can ask for particular metros or cities, and after some agreements are signed, you can have far more data than your server itself provides. You see here that we just get general things like platform, the IP the client came in from, the who is quote-unquote ISP information, date timestamps, up downstream bit rates, latency, and most importantly for our work here, the location in space, latitude and longitude from the mobile device having been reported by the application. And most importantly, connection type, cellular or Wi-Fi. The two shown here, of course, are not on Wi-Fi. So that's kind of the top level, but really we started to scratch below the surface a bit and found out that speedtest.net, in fact, is powered by cats like much of the internet. In the application, you will see this, and we think it perhaps is the whimsy that carries the app on the air. General methodology is that measurements are done against the server from the client through the process you see here. First, a couple round-trip attempts are made over a socket that essentially passes basic headers and nothing more. That's repeated some number of times. And then gets are used to estimate and then finally execute the bulk of the downstream tests, and the same thing is repeated for post methods in the upstream direction. The top 10% of all the 1 second measurements made at the client's socket read or write processes are discarded, as well as the lower 30%. This is to denoise, if you will, bursty behavior, scheduler-related behavior that could mislead the client with regards to exactly how much data was in fact received or sent over the network layer. And then that final result is averaged and reported to the server. So an example server running in Madison, Wisconsin, which is a small region, right, tends to attract clients from areas as far east as perhaps Milwaukee and Chicago, and as far west as Dubuque, Iowa, and parts into northeastern Iowa and eastern Minnesota. And the resulting traffic you see here is not huge, but for such a small market, surprisingly peaky. Diurnal, of course, weighted towards the afternoon, and at no time do we see any single test doing more than a few hundred megabits. So, surprising result. We thought we'd see people with very high-speed connections pegging it for regular periods, but that doesn't seem to happen. Why is it so interesting? I think it's the Gibson effect. The GUIs that the company provides are compelling, not to discredit any other research crowdsourced tools, but these are really sexy. And it seems to be that more of them are ran than any other testing infrastructure I'm aware of. Literally billions per year. So a lot of data. And we want to make use of it, so we're attempting to start on that through a paper that's going to hopefully appear at Conext. I don't mean to jinx it, so look for that perhaps. So let's start looking at some actual numbers. Looking at the prior 5 weeks between February 22nd and the 31st of March, we sampled data from our server. Of course, people on desktop computers, regular browsers, laptops, and so forth outnumber mobiles almost 4 to 1. And accordingly, people are typically almost 2 to 1 using Wi-Fi versus cellular. We thought the ratios would be different, so this is kind of orienting us into a new area. We didn't know that these numbers would be so largely weighted towards more traditional connections. We had assumed mobility, and cellular mobility specifically, was the new thing. So let's filter it a little bit. Of all the servers, or rather of all the traffic that hit the Madison server, only half of it was within one county, within Dane County. The rest of it was everywhere else. Considered a very geographic long tail, if you will. Interestingly, considering how many rows had any one cell, upstream, downstream, or latency tests fail, we find that barely 1/9 is provided, which I guess is surprising to me in that I thought mobile data was even worse. Of the 7,000 or so tests that we received total, about 2,000 were from cellular. So the other ones that had been failing were from a mixture of Wi-Fi and cell. There seems to be no real bias. So currently, Wi-Fi is faster. The data we're looking at here, again, from February to end of March, doesn't include much LTE deployment or 4G deployment because the region we're in is not one of the ones on the top 15 or so sites that Verizon or Sprint or anybody else has enabled yet. We expect to see this trend shift as that happens. So comparing Wi-Fi and cellular, of course, the intuition holds, and it's true that Wi-Fi outpaces cellular. We thought the upstream would be more profoundly different, but in fact, it's barely 3 times. So simple stats. Round trip time tells a different story. Wi-Fi is doing fairly well, but worse than we expected. Cellular is not as good as we had assumed. Our user experiences on EVDO and on HSPA overlays on UMTS, can't say this today, suggest that real round-trip times are much lower than the application is measuring. But for some reason, when all the data is considered with no special filtering other than failure tests being removed, cellular is clearly lagging. Breaking it down into groups of 8 hours, we see a general trend towards lower overall bandwidth, and we see a trend towards higher overall latency, which is perhaps assumed. This is roughly the view of the entire county worth of data. Looking into the city, we see some interesting clusters. Several of these clusters, where you see several dots, orange for cell, green for Wi-Fi, tend to correspond to the same user. And GPS jittering gives us a false sense of population. Interesting stuff. I think personally more interesting things tend to emerge when you start to look at particular cellular carriers as a subset of all of the cellular tests executed. Looking at simply a histogram where the bottommost horizontal axis is megabits per second and the vertical axis represents how many tests were logged at a particular or a given bit rate. We see that AT&T in particular has bimodal distributions, strongly bimodal distributions upstream, and the downstream is a normal distribution. Upstream is generally the more challenged radio link in a mobile network, so we find that the biggest divergence in various network performances are seen there. Again, the horizontal axis is in megabits, and vertical is in test count. AT&T is bimodal. Sprint is generally a linear regression towards unlikelier and progressively unlikelier services. And in the case of Verizon, almost everyone gets half or a third of the upstream available at any one time. It looks like to us, if we didn't know better, T-Mobile is simply unloaded in this market. After some further analysis, it looks like GPS should have a new definition. The application itself is not terribly reliable in that it does not sample multiple times, it does not denoise, does not average. It grabs the first available bit of information from the host's API and is reported. But you know what? Power isn't drained, so that's good. And interestingly, on Android devices, we find that between application execution periods, it might report the same coordinates numerous times, leading us to believe that several APIs perhaps could deserve some additional attention, specifically in terms of data quality with mobility positioning. A quick test confirms it, of course, over a few weeks. Running my iPhone at the apartment, roughly where the yellow pin is located, we see a huge distribution beyond just the normal error reported by the GPS itself. So this leads us to believe that the data collection potential, or rather the analysis potential, is a lot lower than we once thought, given the relative noise of any kind of positional coordinates. And further work is going to be looking at larger aggregates such as U.S. Census Bureau zones or zip codes. More likely Census Bureau, given that's a roughly even population distribution per area. So that is that. I hope you have the carrier you wanted to have.
And we don't have time for questions,
Okay.
and I want to thank Anton very much.
Okay.
And